Our third speaker will be Richard Taylor from the Institute for Advanced Study. So Richard is one of the world's leading experts on a web of conjectures that were introduced in the late 60s and 1970s by Robert Langlands, which have gone on to completely transform how number theorists think about their discipline. And although the field is perhaps more widely respected and feared than understood among the broader mathematical community, it really is motivated by some concrete questions and does have very tangible applications as well. So it's a great honor to have Richard Taylor, who's going to explain to us a bit about the Langlands program.
Thank you, Brian. So I was asked to explain some big problem in mathematics to a general audience. So I'm making an attempt to do that. Now, it may be that, in fact, I don't have a general audience. I have a mathematical audience, which is one way I could fail. Or it may be that I have a general audience and I haven't simplified things sufficiently. But anyway, this is my attempt. So as Brian said, the Langlands program has a long history. You can trace it back to the work of, say, Euler in the middle of the 18th century, certainly to the work of Gauss. But in the 50s, 60s, and 70s, 1950s, 60s, and 70s, it suddenly took on a new lease of life. I guess about 1950, people might have thought that they had sort of got to the end of these ideas, the great achievements of class field theory and so on, and then suddenly it took off again with far more space than the original ideas. Throughout this long history, it's had dramatic applications. And maybe most striking of all is the beauty of the way it brings together completely different areas of mathematics. So I don't think I'm able to convey the breadth of the program very successfully to a general audience. So rather, I'm going to take the approach of trying to illustrate it through some specific problems and hope that these specific examples will give some insight into the general question. So the way I want to present it is the theory of congruences. Some of my work's been done for me because Jacob just introduced congruences. We say that two numbers a and b are congruent modulo a third number p. These are whole numbers, integers. If, and we write a congruent to b modulo p, if p divides the difference, a minus b. So in this talk, p will often be a prime number, which is why I call it p, but at the moment it can be any integer. Oh, wrong way. So for example, an even number is exactly a number that's congruent to 0 modulo 2, and an odd number is exactly a number congruent to 1 modulo 2. Two numbers are congruent modulo 10 exactly when they have the same last digit. 1 is congruent to 13 modulo 12. I put in another example there. Does anybody know why that example is relevant? Probably not. It's the Christian year is congruent. The current Christian year is congruent to the current Muslim year, modulo 17. Anyway, so the last example on this slide is 1 congruent to 13 modulo 12, which is, of course, the basis of the way we tell time. 1300 hours is the same as 1 p.m. And a good way to imagine congruences, if they're new to you, is as a sort of clock. There's no reason why a clock should have 12 hours. It can have any number of hours. So here's a clock with 7 hours. And just as when you first learn to do arithmetic, you do it in elementary school, you do it on a sort of infinite number line. For congruences, you just take that number line and wind it round a circle so it keeps repeating itself, and you do arithmetic in exactly the same way. So for instance, if you wanted to add 4 and 5, you count round 4, get to 4, and then you count 5 more notches round this clock, and you end up at 2. And I've illustrated some typical arithmetic operations here in arithmetic modulo 7. In particular, I've listed the squares modulo 7. You'll see there 0, 1, 4, and 2. We'll come back to this in a little bit, so pay attention. If you run through the 7 numbers modulo 7 and look at the squares, you only find 0, 1, 2, and 4. I'll leave you to do the calculation. Okay, well, why should one care about congruences? Well, today, one might give a number of answers. For instance, they form the basis for the way information is moved about the web, used on DVDs, sent via satellite links, the way we encode vast amounts of information in a way that will protect against small errors and still allow you to recover that information. So it's crucial for much modern technology, but that's certainly not the reason it was originally invented. I don't know when the theory of congruences was first invented. It was certainly known to the Greeks. And the motivation, as I say, was certainly not that. It was, I'm guessing that, or at least one possible motivation was the theory of Diophantine equations. So it's an example of how a topic was originally invented for pure curiosity, for its beauty, but it does in fact find many, many years later, many centuries later, practical applications. So I'm guessing, as I say, that the application, one of the original motivations might have been the theory of Diophantine equations, and I'm going to use the theory of Diophantine equations in this talk as a way to illustrate, as a repeated illustration. So a Diophantine equation is a polynomial equation which one's asked to solve in, I'm going to say, rational numbers, fractions. So something like a third is an allowed solution, but something like the square root of 2 is not an allowed solution. So this is a very old, as I say, a very old topic. It was certainly studied by the Greeks. It's named for Diophantus, who's a Greek living in Alexandria in the 3rd century AD, who wrote a massive tome on it, on the subject, which, except for a small amount of work in India in the 6th and 7th centuries, was really stood as was the up-to-date account of the theory of Diophantine equations for about 1,000 years after it was written. So here is a typical example. Describe all right-angled triangles with hypotenuse 1 and the other 2 sides rational numbers. So by Pythagoras' theorem, what we're looking for is rational numbers x and y such that the sum of their squares is 1. Well, we don't know who first considered this question, but there's a Babylonian cuneiform tablet, nearly 4,000 years old, which lists a whole number of actually rather complicated solutions to this equation. So in the second column, in fact, this just lists the x. I was solving the equation x squared plus y squared equals 1. This tablet lists the possible values of x, or a series of possible values of x, for which there is a y. It doesn't actually tell you the y, but it's easy to find once you know the x. The second column on this tablet gives the numerator of x, and the third column gives the denominator. And here are the same solutions to this equation in modern notation. So, for instance, you see towards the bottom on the left-hand side, the famous 3, 4, 5 right-angled triangle. There's a right-angled triangle with hypotenuse 1 and the shorter sides 3/5 and 4/5. But you get some much more complicated ones with 5-digit numerators and denominators. So it's curious to notice, in fact, that so the first of all these pairs is the one that's listed on the tablet. The second, the one that's not listed, the numerator has a high common factor with 60, or a power of 60. And of course, the Babylonians number system worked to base 60, so to them, all these y's would have looked particularly simple numbers. Well, we don't know how they found this. We don't know if they had a method or it was trial and error. And we don't know why they found it. Was it curiosity? Was it some sort of trigonometric table? As I say, we don't know. But we do know that the Greeks knew how to solve this sort of problem. Of course, x squared plus y squared equals 1, if I let x and y be real numbers, describes a circle. So we're asking for points on the unit circle whose coordinates are fractions, are rational numbers. And there's a very, don't think I have time to describe it for you, but there's a very elementary way to parameterize all such points in terms of rational numbers. Given any rational number t, I draw the line through 1, 0 with slope t, and the second point of intersection with the circle will be a rational point, and this gives a bijection between rational points on the circle and rational numbers t. And in fact, you see, for instance, that the rational solutions are dense on the unit circle, that you can find them everywhere in any little interval. Okay, let me vary this problem now slightly. Let me shrink the circle by a tiny amount, and let's look at solutions to x squared plus y squared equals 0.999999. Now what do we do? Well, you can start looking for solutions. You can try x and y with small denominators. Nothing will seem to work. And in fact, there's a reason for that. There are no rational points on this circle. So geometrically, this looks hardly distinguishable in the real world. But in the world of Diophantine equations, it's suddenly behaving entirely differently. And the explanation for this is the theory of congruences. The mathematician Hendrik Lenstra likes to say that a math talk without a proof is like a movie without a love scene. He obviously thought neither was a very good idea. So here is my the proof for this talk. I'm going to prove this fact for you to illustrate one utility for congruences. So I'm going to assume that there was a rational point, xy, on this equation x squared plus y squared equals 0.999999, and I'm going to get a contradiction. So if there was a rational point, I could write the x and y as fractions with integer, whole numbers numerated and denominator, and I could ensure that the denominator, just by multiplying up, was always divisible by 1,000 if I wanted. And I can ensure that the corresponding a, b, and c have no common factor, because if there was one, I could divide it out. And then substituting this into our equation and clearing denominators, I'm asked to solve the equation a squared plus b squared is 999,999 c squared. And you notice that if I factorize 999,999, there's the factorization. And the key fact for us will be that 7 divides this number exactly once. Now, if this equation holds in the usual integers on the usual infinite number line, it will hold modulo 7, just as Jacob was explaining that you can prove things about the usual integers, or in this case the rational numbers, by generalizing to the ring of integers modulo 7. So I'm going to, if this equation holds, it also holds modulo 7, and I get the equation a squared plus b squared is 0 modulo 7, because 7 divided 999,999. And now I had on my previous slide a list of all the squares modulo 7. They were 0, 1, 2, and 4. So I have an equation 0, 1, or 2, or 4, plus another number of the same form is 0 modulo 7 is divisible by 7. And I can run through the 16 possibilities in no time at all, and only one of them gives 0. If both a and b are 0 modulo 7, then a squared plus b squared is 0 modulo 7. So I've proved if there is a solution, 7 must divide a, and 7 must divide b. So 49 divides a squared plus b squared. But 7 divided 999,999 only once. So another 7 must divide c squared. So 7 must divide c. So I've got my contradiction. They have a common factor, which I could have factored out. Well, so what have I done? I've looked at the particular equation, x squared plus y squared is congruent to 0 modulo 7. And the key fact I used was it only had one solution, x and y both 0 modulo 7. But I can look at any of these equations modulo 7. I mean, I can take 2 has 2 square roots modulo 7, 3 and 4. 1 has 3 cube roots modulo 7, 1, 2, and 4. For instance, 2 cubed is 8, which is 7 plus 1. 4 cubed is 64, which is 63 plus 1. I can look at more complicated equations. Here's a cubic equation in two variables, y squared plus y equals x cubed minus x squared. It has 9 solutions modulo 7, which I list here. Again, this is an example I will come back to. Okay, well, that's congruences. The LANGLANDS program is going to tell us something about congruences in terms of some very different sort of mathematics. And the particular sort of question about congruences it's going to answer is fix an equation or equations in one variable or several variables with integer coefficients, let's say, and let's look at this. When I fix the equation, let me look at the number of solutions modulo a varying prime number p. And the question I'm going to ask is, how does the number of solutions to this equation vary with p? So, as I said, this topic goes back to the middle of the 18th century, when people looked at quadratic equations in one variable. So here's a very simple example. X squared congruent to 5 modulo p. So I'm going to let p be a varying prime number. I'm going to ask, when I do arithmetic on a clock with p hours, when is 5 a perfect square? And I've listed the first 20 primes, well, excluding 2 and 5, which behave a bit differently because they occur in the equation. And for each of the first 20 primes, you see that there are either no solutions or there are 2 solutions, in which case I've listed them. And it's not actually very hard, I think, in this case, to spot the pattern. If you think for a moment, for which primes are there no solutions? Well, there's a prime for no solution exactly when the last digit of that prime in the usual decimal notation is a 3 or a 5. There is no solution modulo 3, 7, 13, 17, 23, 37. When the last digit of the prime p is a 1 or a 9, there is a solution. So modulo 11, 4 squared is 16, which is 5, and so on. So there seems to be a very simple pattern, and this in fact generalizes to all quadratic equations. Oops. Right. There we go. All quadratic equations in in one variable, as I say, was realized in the middle of the 18th century, first by Euler, or as I discovered 2 nights ago, as Keira Knightley says in the new movie The Imitation Game, Euler. And by Legendre. So I should apologize to Legendre for this portrait. According to Wikipedia, this is the only extant portrait of Legendre. In most books, you'll find a much more dignified picture of him. But again, according to Wikipedia, that's actually his cousin. And what they conjectured was proved at the very end of the 18th century by Gauss, 19-year-old Gauss, that for any whole number n, the question of whether n has a square root modulo some prime number p only depends on p modulo 4 times n. So this, to somebody who hasn't seen it before, may not appear very surprising. You've got congruence modulo p and then a congruence modulo 4 times n. It's all the same sort of thing. But I want to stress that really, to me, at least to me, it is extremely surprising fact. Why should trying to find a square root of n on a clock with p hands have anything to do with where p is on a clock with 4n hands? This was supposed to be Gauss's favorite theorem. There are various stories about it. It's certainly true. He came back to it again and again during his life. He gave about 8 proofs, I think. He gave 6 different proofs before anybody else found one. And although I know proofs and I could give a proof to you, none of them seem to have to really explain to me why it should be true. Many facts in mathematics, once you can prove them, it sort of seems obvious. It's the only proof you could give. This is not such a theorem, at least to my mind. There's Gauss. So to illustrate its power, let me take a particular example. Let me ask whether 17 has a square root modulo 20,142,013, which I'll give you is a prime number. Well, of course, with a computer, you could run through the 20-odd million possibilities fairly quickly, but by hand, I guess even Gauss, who was a great calculator, would have had trouble. But using his theorem, you can get the answer very quickly. We know whether 17 has a square root modulo 2014-2013 only depends on 2014-2013 modulo 4 times 17, 68. So when we divide by 68, the remainder is 5. So 17 has a square root modulo 2014-2013 if and only if it has a solution modulo 5. So we're asking whether 17 has a square root modulo 5, whether 2 has, which 17 is 2 modulo 5, 15 plus 2. So we're asking whether 2 is a square modulo 5, and there are only 5 possibilities to try. And if you run through the squares modulo 5, you get 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, which is 4, and 4 squared is 16, which is 1. So 2 is not a square modulo 5. So 17 was not a square modulo 2014-2013. Okay, well, what about equations with more variables? As I alluded to earlier at the beginning of my talk, Gauss's example was a huge motivation to mathematicians throughout the 19th century and into the 20th century. They tried to generalize his theorem. And it led to class field theory, one of the great achievements of the first half of the 20th century. And it appeared about 1950 that somehow the subject had been closed, that it was a beautiful theory, but it had somehow got to the limits of how you could generalize Gauss's law of quadratic reciprocity. But then in 1954, Martin Eichler found a reciprocity law which didn't fit into this mold. In all, the work up to that time had basically been one-variable equations, and not any one-variable equations, only those that were in some sense abelian. Technically, the Galois group involved had to be an abelian group. But then suddenly, as I say, Martin Eichler found an example which certainly wasn't abelian. It was two-variable. In fact, it was a cubic equation in two variables of this form. Y squared plus some constant times y is a cubic equation in x, where these coefficients, a, b, c, and d, are all fixed. And he found such a law. So let me describe this to you. I'm going to write NP for the number of solutions. And I'm going to take this example that I had a minute ago. Y squared plus y equals x cubed minus x squared. And I said it had 9 solutions modulo 7. And I calculated it for a number of other small primes. So if it's about 8 primes or something, and the number of solutions to this cubic equation in two variables modulo each of them. And the first thing you'll notice is that it doesn't seem to be like a quadratic equation in one variable. The number of solutions seems to be growing with the primes, and that's indeed the case. Hasse proved in 1933 that the number of solutions to this equation modulo a prime p was approximately p to within an error that was bounded by twice the square root of p. So the leading term was p, and then there was a smaller error. And one can ask the question, so more natural then is to study the error rather than the leading term, which is rather simple. So we're going to study the difference between p and the number of solutions to this congruence modulo p. So I've tabulated that. And now I'm going to predict the same thing from a completely different point of view. I'm going to consider the infinite product that I've written there in an indeterminate q. So q is just some indeterminate quantity. I take q times 1 minus q all squared, and then 1 minus q to the 11 all squared, and then 1 minus q squared all squared, and 1 minus q to the 22 all squared, 1 minus q cubed squared, and so on. Of course, the product goes on forever, but if I'm only interested in the coefficient of q to the 10 or something, I only need to take finitely many terms in this infinite product, so I can start multiplying it out. And it takes quite a lot of work, but there are the first 20 terms in this product. And to my mind, another quite remarkable thing happens. if I look at the coefficient of q squared, it was -2, which was exactly the error in the point count modulo 2. If I look at the coefficient of q to the 7th, it's -2, which again is exactly the error in the point count modulo number of points on this curve modulo 7. So on the error n19 was exactly 19, the coefficient was 0, and you see that q to the 19 doesn't occur in this expansion. And that's not a coincidence for the first few primes. So I say Martin Eichler proved in 1954 that this will be true for all primes p for this cubic equation in two variables. And this opened the floodgates. Within a year or so, people were beginning to believe this was a much more general phenomenon. So Taniyama suggested that in some sense the same thing should be true for any cubic equation in two variables. Shimura made it a bit more precise a couple of years later. Wei, a decade later, really nailed it down, precise form of the conjecture. And I say there's some similar, they propose some similar algorithm for calculating producing these counting the number of solutions to such a cubic equation modulo p. It does not involve, in general, an infinite product. I chose this infinite product, firstly, because it was the case that Eichler studied, and secondly, because it was easy to explain. But that's not how it generalizes. To generalize it, similar means I should think of this as a function of q. This infinite product actually converges when q is a complex number of modulus less than 1. So I can think of this as a function on the interior of the unit disk in the complex plane. Picture of the complex plane, or the unit disk in the complex plane. Now, the unit disk has certain symmetries. It's a model for the so-called hyperbolic plane. In particular, SL2Z, the set of 2 by 2 matrices with integer entries and determinant 1, acts on it. And this function, the key thing about the function is not that it has this infinite product expansion, but when I think of it as a function on the hyperbolic plane, in the interior of the unit disk, it's very symmetric. This is a very symmetric function, and that's the generalization. There should be an algorithm to calculate the number of solutions to such a cubic congruence modulo number p, which involves somehow the group of 2 by 2 matrices with integer entries and its action on the so-called hyperbolic plane. So there's another picture of the hyperbolic plane to give you some idea of what it looks like. All those regions, white and black regions in this picture, are triangles. So in this hyperbolic geometry, some of these things that look like curved lines to us are in fact straight lines. And all those triangles are the same size in this hyperbolic world. So although to our eyes they look very tiny as they go out towards the boundary of the disk, in the hyperbolic world, space is spreading out very rapidly, so they could be considered the same size. This sort of geometry also came up. It was communicated to the artist Martin Escher by Coxeter, the mathematician Coxeter, and he used it in some of his woodcuts. Well, we now know this is true. It was proved beginning of this century, following ideas introduced by Andrew Wiles. And again, it has Diophantine applications. This case famously to Fermat's last theorem. As probably most of you know, in the middle of the 17th century, Fermat wrote in the margin of his copy of Diophantus, his book on Diophantine equations, that no cube could be written as the sum of two cubes, no fourth power the sum of two fourth powers, and so on, for any power greater than 2. He claimed to have a proof that he couldn't fit in the margin, and nobody could find a proof until Andrew Wiles at the end of the 20th century. So this was the theorem that Wiles proved. And how he proved it was exactly via a reciprocity law. In fact, a few years earlier, Gerhard Frey and Ken Ribot had established that if Fermat's theorem was wrong, you could write down a cubic equation that did not satisfy the Shimura-Taniyama conjecture, this reciprocity law for cubic equations in two variables. So modulo some permuting of A, B, and C, this particular cubic equation will do. And what Wiles did was he proved certain reciprocity laws. So again, it's a case that reciprocity laws are telling us things about Diophantine equations that couldn't be obtained by other means. The people involved. Well, it doesn't stop at cubic equations in two variables. Within another decade or two, Bob Langlands had realized it should apply to any number of equations in any number of variables of any degree. And the answer should again depend on symmetries in certain geometries. So it was a connection on the one hand between solving polynomial equations modulo n, this algebraic system of solving equations in certain rings, and on the other hand, some geometry, symmetries in usually high-dimensional geometries and non-traditional geometries where the space is curved. So I can't, even for SL3, so again, there's an action of n by n matrices with integer entries and determinant 1. And we have to consider all n. Already for n equals 3, I have to consider a 5-dimensional geometry that I can't illustrate. So instead, I will talk about SL2, working over the Gaussian integers, z adjoin the square root of -1. There you get a 3-dimensional geometry, which I may be able to illustrate. Oops. No, maybe I can't. Here we go. This was a movie made by people at the University of Minnesota, which is moving through hyperbolic 3 space. So you may notice various things. First of all, the space is tessellated by dodecahedra. You can't tessellate normal space by dodecahedra. The second, again, there's this phenomenon that as you move through, things from the outside come towards you at a different rate. The space collapses towards you at a different rate than you would as if you were moving through usual Euclidean space. So again, it's symmetries in spaces like this which should determine the solubility of these equations. And today we know, this slide just tells us the generality in which we now know these reciprocity laws. There's much greater generality. We can look at varieties of any dimension. There's still a very strong restriction, it appears to be a very strong restriction called regularity. A geometer would be horrified, although somebody working in automorphic forms would maybe say it was the generic case. It's a sort of strange situation. But anyway, we know much more, but there's an awful lot we don't know. For instance, there's some example of a particular higher degree equation in lots of variables for which we know a reciprocity law. Okay, I want to finish with a final I'm running out of time. Final Diophantine question, another old one that goes back to the 10th century. The mathematician Al-Karaji, who worked in Baghdad, posed the following question. For which whole numbers n is there a right-angled triangle with area n, all whose sides have fractional length? So again, this is a problem. We want a triangle area n, sides x, y, and z are all rational numbers. So we've got to find x, y, given n, we've got to find x, y, and z with x squared plus y squared equals z squared, and n equals x, y over 2. So again, it's not very clear how you would go about doing this. I mean, given, say, you give 1, you try, say n was 1, you want a right-angled triangle area 1, you could try x, y, and z with small denominators, see if you could find any examples. You would find that you couldn't find any. But what does that mean? Well, we now believe we know how to answer this question. Instead of the original problem, let me take this putative area of the triangle n and try and write it as a perfect square plus twice a perfect square plus 8 times a perfect square. And for simplicity, let me suppose n is odd and square free, just so you can do the other cases too. Well, that's an easy thing to calculate because the solutions u, v, and w have to be bounded by the square root of n. So there are only finitely many possibilities you can easily run through. And then I'm going to count the ones for which w is even. and the ones for which W is odd, and write that AN even and AN odd. So two things that are easy to calculate given N. And what we believe to be true is that there is a right-angled triangle with fractional side lengths and area N, if and only if AN even is equal to AN odd. So this is a computable criterion now. Well, we don't know this, but we know half of it. We know if AN even and AN odd are different, there's no such triangle. This was proved by Jerry Tunnell, Dick Gross, Don Zagier, and Victor Kolyvagin in the 1980s. And again, their proof was based on a reciprocity law. It was based on Artin's reciprocity law from the first half of the 20th century. In fact, this happens to be an abelian reciprocity law. In the sort of ubiquity of reciprocity laws in Diophantine equations. And the people involved. So here are some examples. For instance, if n equals 1, AN even is 2, AN odd is 0. So we know by this Kolyvagin's theorem that there's no such triangle. That's not news. In fact, that was proved by Fermat in about 1640. Again, for n equals 3, there's no triangle of area 3 there's no triangle of area 3 with rational sides. But for n equals 5, AN even is AN odd, which is 0. So there is we believe, but don't immediately know, that there is a right-angled triangle with area 5 and rational sides. And in fact, that's not news either. It was found by Fibonacci in about 1200. It's not terribly complicated. It has sides 9, 6, 46, and 41, 6. But now if we let the numbers get a bit bigger, just go up to 100, look for triangles of area 155, 157, 159, and so on. Well, we see that Kolyvagin's theorem tells us that there's no triangle of area 155 or 163, which wouldn't be so easy to determine any other way. But we expect there are triangles of area 157, 159, and so on. Richard Feynman, in his book, You Must Be Joking, Mr. Feynman, said that when he was a graduate student in Princeton, he used to like to tease the mathematicians. He could say he could answer any problem they gave him. He didn't promise to find a proof, but by calculating some examples or guesswork or psychology, he could always answer their questions, and he claimed that he was undefeated. I wish somebody had asked him, given him, say, the numbers 155 or 165, and asked him for which such numbers there's a triangle with right-angled triangle with rational sides in that area. I don't think it would have been so easy without knowing this theory and this reciprocity laws to figure such a thing out. For instance, in the case of 157, Don Zagier found the simplest such triangle. But the Jerry Tunnell's method predicted this very beautifully and very quickly. Okay, I'll stop there.
So we have time for some questions. Yeah.
How much do you use of computers in your own research?
In my research, I don't use them at all. Although, I mean, that's my lack of ability. As I said this morning, they've certainly had an influence. This particular question is the fact that we know that answer. It's a special case of the Birch-Swinnerton and Dyer conjecture, which I also mentioned this morning, which arose through numerical computation. So it was numerical work of Brown, Birch, and Peter Swinnerton and Dyer that, I mean, and oops, that's not, what am I supposed to do here? Now I've got.
Do you want to pull it up again?
No, I'm on the wrong end though. Well, okay, it's hopeless. This conjectured explanation for when there's whether AN odd equaling AN even predicts whether there's a right-angled triangle. As I say, that's an explicit version of the Birch-Swinnerton and Dyer conjecture for a particular elliptic curve. But but even to think about it in the right way, to formulate it like that, relies on ideas that were inspired by beautiful numerical computations.
Any questions? None? Okay, let's thank Richard again.